Welcome to the Beauty of Math channel. Please subscribe for more about math.
Let's break down this advanced calculus problem step by step from the absolute beginning so we can see exactly what we are dealing with. We start by defining our entire integration problem as the variable capital I. We have a definite integral starting from a lower limit of 0 all the way up to an upper limit of pi over 2. Now look closely at the main fraction inside the integral. In the numerator, we have e raised to the power of sine x. This is placed over a denominator consisting of two terms added together, e to the power of sine x plus e to the power of cosine x, and everything is multiplied by the differential, dx, at the end. If you try to approach this using standard integration techniques, you will quickly see why this problem is legendary on advanced university entrance exams. Think about that numerator, e to the power of sine x. There is no standard, clean, elementary antiderivative for this term on its own. If you try a regular u substitution, or if you attempt integration by parts, the expression will spin completely out of control, getting larger and more complicated with every single step. It looks like a mathematical trap. But instead of trying to compute the antiderivative directly, smart students use a brilliant shortcut that completely bypasses the hard calculus. To crack this wide open, we use a beautiful principle known as the King's property of definite integrals. The formula on screen states that integrating a function, f of x, from a lower limit a to an upper limit b yields the exact same numerical result as integrating that same function when every single x is replaced by the sum of the limits minus x, written as a plus b minus x. For our specific problem, our lower limit a is 0. And our upper limit b is pi over 2. When we add 0 and pi over 2 together, we just get pi over 2. Therefore, this property tells us that we can replace every single x in our original expression with the term pi over 2 minus x, and the total value of the integral, capital I, will remain exactly the same. Let's perform this substitution step by step and look at our new expression for capital I. Our integral boundaries stay exactly the same, from 0 to pi over 2. But look at how the fraction transforms. In the numerator, we now have e raised to the power of sine, evaluated at pi over 2 minus x. Now look down at the denominator. The first term becomes e raised to the power of sine, evaluated at pi over 2 minus x. This is added to the second term, which is e raised to the power of cosine, evaluated at pi over 2 minus x. Don't forget our dx at the end. Now, we apply basic trigonometry cofunction identities to clean this up. We know that the sine of pi over 2 minus x simplifies perfectly into cosine x. And conversely, the cosine of pi over 2 minus x simplifies perfectly into sine x. Let's substitute those simplified terms back into our fraction. Our new numerator becomes e raised to the power of cosine x. Our new denominator becomes e raised to the power of cosine x plus e raised to the power of sine x. We now have a brand new equation for capital I. And notice something incredible. The denominator of this new integral is exactly identical to the denominator of our original integral. Since both equations are perfectly equal to capital I, let's add them together. On the left side of our screen, I plus I gives us 2i. On the right side, because both integrals share the exact same denominator, we can combine them into a single integral running from 0 to pi over 2. When we add the two fractions together, look at our new numerator. It is e to the power of sine x plus e to the power of cosine x. And look at our shared denominator. It is also e to the power of sine x plus e to the power of cosine x. The numerator and the denominator are completely identical. This means the entire massive, terrifying fraction cancels itself out perfectly, leaving us with just the integral of 1 dx. The integral of 1 with respect to x is simply x. When we evaluate x from our lower limit of 0 to our upper limit of pi over 2, we get pi over 2 minus 0, which is just pi over 2. Remember, this value equals 2i. So, to find our final answer for our original integral, we simply divide both sides by 2. 2i equals pi over 2, which means capital I equals pi over 4. A problem that looked absolutely impossible is solved cleanly without ever finding a complex antiderivative. Symmetrical beauty at its finest. Thank you for watching. Don't forget to subscribe for more about math.